Thank you. Good morning, everyone. I'm Yuanpeng Zhang from Peking University. I'm going to introduce our work, AIM, Software and Hardware Co-Design for Architecture-Level Airdrop Mitigation in High-Performance PIM. SRAM PIM has emerged as a promising architecture for high-performance computing, offering exceptional computing density, energy efficiency, and computational precision. SRAM PIM architectures can be categorized into two types, analog PIM and digital PIM, based on their data accumulation format. Although they are different in the form of product accumulation, they share similarities in data placement and processing paradigm. We call the multiplied data stored in SRAM as in-memory data, and the serialized data sequentially loaded on the word line as input data. Airdrop represents the voltage discrepancy between the ideal voltage supply and actual voltage received by each circuit cell. Its magnitude is positively correlated with the product of current passing through the power delivery network, I, and the resistance, R. Airdrop can be classified into static airdrop and dynamic airdrop. Static airdrop is caused by leakage current, such as current leakage through transistors in the off state. Dynamic airdrop is caused by dynamic current, which occurs when the integrated circuit is in operation. It mainly consists of short circuit current and switching current. Dynamic airdrop is thus highly sensitive to runtime activities, including gate switching and the capacitive charge and discharge cycles. As chip performance advances and frequency increases, the airdrop problem is becoming more and more serious. Significant airdrop reduces the voltage to sender cells, leading to time violation. To address this, IC designers always use numerous time-intensive and costly circuit-level mitigation techniques, compromising the chip's performance, power, and area. Fortunately, our airdrop profiling of a high-performance PIM reveals an opportunity. While airdrop changes during processing, the actual worst airdrop remains considerably lower than the sum-of worst case, which means circuit-level mitigation may be too passive. Furthermore, in-situ data flow and bit serial multiplication of PIM make the data behavior model more observable. Therefore, the key to architecture-level airdrop mitigation is identifying and exploiting the relationship between workloads and airdrop. Commercial tools commonly use gate-level bit toggle rates to evaluate circuit-level airdrop. Inspired by this, we propose our toggle to correlate software workload and hardware airdrop. Our toggle quantifies the cycle-to-cycle toggle rate of bit streams from SRAM cells to the adder tree. The experiment's results show that our toggle correlates strongly with airdrop, so it is possible to mitigate airdrop through our toggle. However, our toggle changes with input streams. It is infeasible for runtime analysis. Based on the observation that when the weight is 0, output bit never toggle. We introduce HR, the Hamming rate of weights. Hamming rate equals the number of valid bits divided by the total number of bits in the quantized weight. The experiment's results show that Hamming rate dominates the maximum of our toggle, and HR optimization reduces overall our toggle. Further, Hamming rate is only decided by preloaded data, and so we can achieve architecture-level airdrop mitigation by optimizing the Hamming rate of weights. Based on our toggle and Hamming rate, now I will introduce the AIM design. During off-chip preprocessing, the weights are optimized by lower Hamming rate, weight distribution shift, and finally mapped onto PIM macros by HR-aware task mapping. During runtime, IR Booster dynamically selects optimal voltage frequency pairs for each PIM macro, thus enhancing energy efficiency and chip performance. The Hamming rate value is a non-differentiable integer metric, and thus cannot be directly used in quantization. So, in lower Hamming rate, we use linear interpolation to approximate the Hamming rate of a floating point weight. And we penalize layers with higher Hamming rate using loss function with corresponding regularization term. Experiments show that lower Hamming rate encourages weight to align with local minima of the Hamming rate. Furthermore, we find that quantized weight remain normally distributed and negative values with smaller absolute magnitudes exhibit higher Hamming rate. So we realize that shifting the data distribution towards positive values can help further reduce overall Hamming rate. Therefore, we introduce weight distribution shift, adding all weights a constant value, delta. After weight distribution shift, there are more weights in lower Hamming rate area. However, delta leads to an computational error to the results, so we design shift compensator to alleviate the error while ensuring the correction stays off the critical path. Shift compensator is located next to PIM macro banks, sharing input streams to optimize resources usage. It performs three main operations: correction calculation, correction term broadcast, and correcting. Experiments show that lower Hamming rate and weight distribution reduces the Hamming rate of weight. However, different models, even different layers from the same model, achieve different optimized Hamming rate. The dynamic mitigation requirements motivate us to propose a hardware-based technique to fully utilize the Hamming rate optimization. IR booster allows macros to operate at lower voltages and higher frequencies. Specifically, IR booster first reserves voltage-frequency pairs for different R toggle, ensuring safe operation across corresponding airdrop during hardware design sign-off. Then, during compilation, IR booster gathers the weight Hamming rate information for each macro after task mapping is completed. Since Hamming rate represents the upper bound of R toggle, the safe VF pair for each task is determined during preprocessing. At runtime, IR booster can aggressively adjust the voltage and frequency, while maintaining chip reliability through a hardware-based IR failure detection and recalculation mechanism. Different networks and operators achieve different Hamming rate, and in PIM chips supported by IR booster, once a weight is assigned, each macro has its own safe VF pairs, which means any naive mapping will lead to suboptimal performance. Therefore, we propose HR-aware task mapping. It is integrated into the compiler to optimize task to macro mapping before inference begins. An absolutely optimal mapping does not exist because of unknown input features, so we design it based on simulated annealing. Thereby, software-based HR optimization methods and hardware-based IR booster are connected. They work in concert to deliver optimal improvements. Here is our evaluation. The hardware configuration is 2 RISC-V cores and 16 macro groups. Each group contains 4 macros. And we select various models to demonstrate the generalizability of our work. Software experiments results show that lower Hamming rate and weight distribution shift lead to substantial HR reduction with minimal impacts on accuracy. We evaluate AIM's overall performance on our 2056 TOPS PIM design utilizing post-layout simulation, a widely recognized hardware simulation method. And the results show that AIM can achieve great airdrop mitigation, energy efficiency optimization, and performance improvement. We conduct an ablation experiment to analyze the contribution of each component of AIM. Under transformer-based workloads, the primary improvements are from IR booster, and for convolution-based workloads, lower Hamming rate provides the main benefits. This is because For transformer-based workload, Q, K, and V matrix are all related to the user input, preventing software optimization. In contrast, convolution operators are predetermined, so software optimization works better. And HR-aware task mapping always better than those naive mapping methods. To summarize, in this work, our goal is architecture-level airdrop mitigation through software-based Hamming rate optimization and hardware-supported runtime adjustment, avoiding the passive of circuit-level airdrop mitigation techniques. To this end, we first propose our toggle and Hamming rate of weights to correlate workload and airdrop. Based on our toggle and Hamming rate, we propose AIM, software and hardware co-design for architecture-level airdrop mitigation. And finally, we conduct experiments to prove AIM's performance. Okay, that's the end of my talk. Thank you for your listening, and I'd be happy to take any questions you may have.